Breakthroughs in physics and materials science, unveiling the quantum and cosmic frontiers. The realm of physics and materials science stands at the precipice of profound transformation, driven by discoveries that bridge the microscopic quantum world with the vast cosmic scales. As of September 2025, researchers are unraveling mysteries that challenge long-standing theories and promise revolutionary applications in technology, energy, and our understanding of the universe. From nanoscale structures that could redefine nanotechnology to geometric phenomena warping electron behavior and cosmic observations hinting at black holes as engines of dark energy, these breakthroughs exemplify the interdisciplinary synergy between physics and advanced materials. This essay delves into three pivotal advancements: the discovery of gold quantum needles, the observation of quantum geometry in real materials, and insights from the Dark Energy Spectroscopic Instrument, DESI, suggesting black holes generate dark energy. By exploring their scientific underpinnings, related concepts, real-world examples, and potential implications, we illuminate how these innovations are reshaping our world. Gold quantum needles, pioneering anisotropic nanostructures for nanotechnology. In the intricate domain of nanotechnology, where materials are engineered at the atomic scale to exhibit extraordinary properties, a groundbreaking discovery has emerged: elongated, pencil-shaped gold nanoclusters dubbed gold quantum needles. Unveiled by researchers at the University of Tokyo in early September 2025, these structures represent a novel form of gold nanoclusters formed through an unconventional nucleation and an isotropic growth process, ScienceDaily.com. Unlike traditional spherical or cubic nanoclusters, these needles are composed of repeating units of triangular trimers and tetrahedral tetramers, creating a highly elongated morphology with an extremely thin diameter, on the order of a few nanometers. Fizdog. This pencil-like shape arises from a self-assembly mechanism during the synthesis of gold nanoclusters. Under specific chemical conditions, where gold atoms organize into linear chains stabilized by ligand molecules, such as thiolates, that prevent aggregation into more isotropic forms. The unique properties of gold quantum needles stem from their quantized electronic structures, a hallmark of quantum confinement effects in nanomaterials. Due to their slender dimensions, electrons within these needles experience severe spatial restrictions, leading to discrete energy levels rather than continuous bands, akin to particles in a one-dimensional box in quantum mechanics. This results in enhanced plasmonic resonances, collective oscillations of electrons that interact strongly with light, making the needles exceptionally efficient at absorbing and scattering specific wavelengths. For instance, in optical spectroscopy experiments, these structures demonstrated sharper absorption peaks compared to bulk gold or spherical nanoclusters, potentially improving resolution in imaging techniques by factors of 10 or more gadgets through 60.com. Moreover, their anisotropic nature allows for polarized light manipulation, where the needle's orientation dictates the direction of light interaction, opening doors to advanced photonic devices. Relative to broader materials science, gold quantum needles build on decades of research into noble metal nanoclusters, which have been pivotal in catalysis and sensing since the 1990s. For example, earlier gold nanoparticles were instrumental in the development of surface-enhanced Raman spectroscopy, SRRs, amplifying molecular signals for detecting trace chemicals in biomedical diagnostics. The needles extend this legacy by introducing directionality. Imagine using them in targeted drug delivery systems, where the elongated shape facilitates penetration through cell membranes guided by external magnetic or light fields. In energy applications, their superior light harvesting capabilities could boost the efficiency of dye-sensitized solar cells. A hypothetical example: integrating gold quantum needles into perovskite solar panels might increase conversion efficiency from the current 25% to over 30% by enhancing charge separation through plasmonic hot electron injection. Lifeboat.com challenges remain, however. Synthesizing these needles requires precise control over reaction conditions, such as temperature and ligand concentration, to avoid unwanted branching or aggregation. Scalability is another hurdle. While lab-scale production yields micrograms, industrial applications demand grams or kilograms. Yet, the potential to revolutionize nanotechnology is immense. In medicine, these needles could enable ultra-high-resolution imaging for early cancer detection, where their quantum properties allow for non-invasive, real-time visualization of tumors at the subcellular level. Interestingengineering.com. In electronics, they might form the basis of next-generation transistors with reduced power loss, leveraging their one-dimensional electron transport to minimize scattering. As researchers continue to explore variations such as alloying with silver or platinum, these gold quantum needles herald a new era of anisotropic nanomaterials, blending physics quantum principles with materials. Engineering's practical ingenuity. Quantum geometry observed, distorting electron paths in real-world materials. At the heart of quantum physics lies the enigmatic concept of geometry, not the Euclidean spaces of classical mechanics, but a profound quantum geometry that governs the behavior of particles in exotic materials. In a landmark observation reported in September 2025 by scientists at the University of Geneva, researchers have directly visualized a quantum metric in real materials, revealing how it distorts electron trajectories in ways reminiscent of general relativity's space-time curvature. ScienceDaily.com. This quantum metric, the real part of the quantum geometric tensor, quantifies the distance between quantum states in momentum space, influencing how electrons navigate band structures in solids. Previously confined to theoretical models, its experimental detection in materials like topological insulators and Weyl semimetals marks a pivotal shift with profound implications for electronics and superconductivity. The discovery was achieved using advanced techniques such as angle-resolved photoemission spectroscopy, ARPS, combined with intense laser pulses to probe electron dynamics. In these experiments, electrons in materials exhibiting spin-momentum locking, where an electron's spin aligns with its direction of motion, experienced path distortions under the influence of the quantum metric. Much like how massive objects in Einstein's gravity warp light paths, this metric bends electron wave functions, leading to anomalous velocities and Hall-like effects without external magnetic fields. Science.org. For example, in a bismuth-based topological insulator, electrons deviated from straight-line trajectories by up to 20% in simulated models, a deviation confirmed experimentally through time-resolved imaging that captured the warped paths in femtoseconds. ScienceDaily.com. This observation ties into broader quantum materials research, including the study of Berry curvature, a related geometric phase that drives phenomena like the quantum anomalous Hall effect observed in thin films of chromium-doped bismuth selenide since 2013. The quantum metric extends this by incorporating higher-order effects, potentially explaining discrepancies in high-temperature superconductors like cuprates, where electron pairing defies conventional BCS theory. In correlated electron systems, such as those with strong electron-electron interactions, the metric could trigger local moment swap-over, where magnetic moments flip under geometric influences, as proposed in recent ARCF preprints, arxiv.org. An illustrative example is in ultrafast electronics. Devices exploiting this distortion could achieve switching speeds beyond petahertz frequencies, far surpassing current silicon-based transistors limited to terahertz. Imagine quantum metric-enhanced photodetectors in 6G communications, where warped electron paths enable ultra-sensitive signal processing with minimal energy loss. Yet, observing and harnessing quantum geometry poses challenges. The effects are subtle, requiring cryogenic temperatures and high vacuum environments to minimize thermal noise. Materials must be engineered with precise doping to amplify the metric, as seen in recent syntheses of twisted Balea graphene, where moire patterns induce artificial geometries. Ethically and practically, these advancements raise questions about scalability for consumer tech, but their words are tantalizing, revolutionizing superconductivity for lossless power grids or enabling fault-tolerant quantum computing by stabilizing qubits through geometric protection. As physics probes deeper into quantum matter's geometric heart, this discovery not only validates theoretical predictions, but also paves the way for a new class of geometric electronics, where material design manipulates electron paths as deftly as architects shape buildings. Science springs. WordPress, Dark Energy Insights. Black holes as cosmic generators, challenging universal expansion models. Shifting from the quantum nanoscale to the cosmic expanse, the Dark Energy Spectroscopic Instrument, DESI, has delivered tantalizing evidence as of August 2025 that black holes may be the elusive source of dark energy, upending our understanding of the universe's accelerating expansion. DSI, a massive survey mapping over 35 million galaxies and quasars, has observed that the density of dark energy appears to evolve over time, inconsistent with the constant cosmological constant proposed by Einstein's general relativity phys.org. In a bold hypothesis, researchers propose the cosmologically coupled black hole (CCBH) model, where supermassive black holes at galactic centers convert infalling matter into dark energy, providing a dynamic explanation for the universe's engine desi.lb allowed. Under the CCBH framework, black holes formed from the collapse of massive stars do not singularly evaporate via Hawking radiation, but instead tap into the gravitational field, gradually transforming baryonic matter into a dark energy component. This process aligns with DESI's 3-year data, which shows dark energy's influence waning in the early universe and strengthening today, potentially resolving the Hubble tension, a discrepancy in expansion rate measurements between local and cosmic microwave background observations, scitechdaily.com. For instance, in simulations incorporating CCBH, the universe's acceleration matches DESI's baryon acoustic oscillation BAO patterns, where galaxy clustering reveals dark energy's imprint, with black holes contributing up 10% of the total dark energy budget by converting stellar remnants, news.umic.edu. This insight relates to long-standing puzzles in cosmology, such as the nature of the 68% of the universe attributed to dark energy since the 1998 supernova observations. Traditional models treat it as a vacuum energy inherent to space-time, but DESI's hints of evolution suggest alternatives like quintessence fields or modified gravity. The black hole mechanism elegantly integrates with general relativity by positing non-singular interiors, perhaps fuzzy balls of dark matter, avoiding information paradoxes. An example from DESI data. Quasars with central black holes show correlated expansion rates, implying dark energy leaks from accretion disks, boosting neutrino masses to positive values consistent with oscillation, experiments like Catherine.Durham, OSHAC.UK. By project's end in 2026, DESI aims to map 50 million objects, including those with black hole cores, refining this model. Implications extend to materials science through exotic matter analogues. Understanding dark energy generation could inspire metamaterials mimicking cosmic repulsion for anti-gravity applications. Challenges include verifying CCBH via gravitational wave detections from LIGO, as merging black holes might emit distinct signatures. Nonetheless, if confirmed, this reshapes cosmology, portraying black holes not as cosmic dead ends, but as perpetual engines fueling the universe's fate, eternal expansion, or potential Big Rip Ducts Innovation News Network. Conclusion: interconnected horizons in physics and materials. These 2025 breakthroughs in gold quantum needles, quantum geometry, and dark energy insights underscore the interconnected tapestry of physics and materials science. From nanoscale engineering that harnesses quantum confinement to geometric manipulations of electrons and cosmic revelations linking black holes to universal dynamics, each discovery expands our toolkit for innovation. As we integrate these into applications, from efficient solar cells and superconducting circuits to refined cosmological models, these advancements promise a future where quantum precision meets cosmic scale, driving sustainable technologies and deeper existential insights. Yet they remind us of the humility required in science. Each revelation begets new questions, propelling humanity toward an ever-enlightened horizon.